Hi, everybody. My name is Tanya, and I will be the moderator of today's event. Thank you all for joining us and supporting what is the first event powered by Intertec that goes under the name Tech Tuesdays. Just to give you a brief description about the idea behind these events is to bring closer as well as encourage and inspire knowledge transfer among IT professionals here in Macedonia and beyond. Anyone is welcome to join us, ask questions, and see how we bring ideas to life. On the other end, from my left is Goran Kopevski, a dear colleague of mine and today's presenter. He will be talking on the topic data pumping, road from MySQL to DynamoDB. Just to give you a short description about his tech background, Goran is a senior JavaScript developer who is part of the JavaScript Guild here at Intertec and is currently working as a tech lead for Intertec's biggest clients, GSG. So not to drag this any longer, Goran, hi, and let's get this thing started.
Thank you, Tanya, for the introduction. So let's start. First, I will share my screen. I will start with the presentation. I hope that you see my presentation. So first, one more time, thank you all for joining. Today, I'm going to speak about data pumping, road from MySQL to DynamoDB. As part of our JavaScript Guild, just first to give an explanation what is JavaScript Guild. In our company, we have basically multiple groups of people who share common interests, and we often share knowledge between ourselves. And one of the topics in the last month was to present this presentation because we find it interesting and a little bit non-conventional, non-classic development about how you can migrate data between the databases. So let's start. As I mentioned, I'm going to speak about data pumping, route from MySQL to DynamoDB. First, a short info about myself. This is me on the image. I'm Goran Kopevski. I work as a tech lead. I worked as a tech lead at Intertec. Oops, wait. As a tech lead at Intertec, I've also worked as a tech lead for our client GSG. I have 9 years of experience, active development. I have worked on a lot of systems. And basically, this is the latest thing which I'm working. I would like to share with the developers in Macedonia. Also, if someone is joining from abroad. So let's start. This is the agenda. I have divided the agenda into two. That means that how I have created the agenda was that on the right side, you can see that I have multiple questions. So basically, these are the questions that we will try to answer with the agenda from the left. That means that we want to see where are we, where we want to be, what is our problem with the situation, how to get there. Basically, I'm going to explain the solution that we will trying to that I will try to present today in multiple steps, where I will show with all of the pros and cons with each iteration of the solution. And as soon as if we can implement the solution, I'm going to show you how we try to improve ourselves and how to continue the momentum. So let's start. The inspiration for this presentation and basically for this talk was from Building Microservices. This is a book from Sam Newman. I highly recommend to everyone who is interested into building scalable systems. And there is one chapter in the book where he talks about data pumping. And basically the general idea was taken from that book, and also we have enriched with the AWS infrastructure, because that is the tools that we are using in GSG. So let's start. This image represents our old architecture. I'm gonna go step by step, and I'll try to give context on every piece of the architecture. Also, this is a simplified version, but just to get a general idea about how our system works. So let's start. The first part is that actually we are serving the application through CloudFront, and we have an application. The data source for the application is a MongoDB. From MongoDB, we have an application which we call Sync application. And that application basically is syncing the data from Amazon RDS, which is SQL, to MongoDB. I'm going to explain later why we are using it like that. And basically, on the other side, we have an administration panel, the Angular part, where the editors or the editors who are working on inserting the content on our web pages are inserting the data into RDS. Also, the top right part is the microservices. Basically, this is two examples of microservices that we had initially started. We have a DynamoDB table. We have a Java application, which is deployed on an Elastic Beanstalk through API gateway, feeding the Sync application. So now to give you a context for what kind of application I'm talking about. I'm talking about an application which serves coupons. So for example, if you want to buy something on Amazon or any other place, before you check out, there is usually a small place where you need where you have a text box where it's usually saying insert a coupon here. And if you type, for example, in Google and you go something like coupon Nike shoes, Amazon, that you want to buy them from Amazon, usually there will be multiple results on your Google SERP. And usually one of the top 3 choices on the page, of course, where we have our applications, it's usually our web pages. So now let's go with the problem. So basically, we have here the MongoDB, and we are serving the data from MongoDB to the application. Why we have choose Mongo? The reason for that was that we wanted to have the fastest possible way, because one of the major things if you want to rank on Google is to be fast. So basically, here we had all of the schemas, all of the tables from Amazon RDS, basically copy-paste to MongoDB, and also with the extra information from the 2 microservices. Initially, this looks totally okay, and it can serve pretty good if you're working with one application. But now let's talk about multiple application. Our architecture initially and currently still running in production has an Amazon RDS per country. In total, we have around, at the moment, we have around 50 clients. By clients, I mean applications that we are serving. And we have around 10 countries where we have the data, where we have the Amazon RDS. That means that we have 10 sync applications, and that means that we have 10 Mongos. And now the bad part is that we have multiple EC2 instances, which is serving the application. So the first thing that we can notice here, what the problem is that actually we need to maintain multiple MongoDBs, and we need to have a multiple sync application. To make the problem even bigger, the sync process is happening once per hour. That means that the users usually are getting, the end user usually can get the data up to 1 hour, up to 1 hour late. So that means that our application it's not in the best scalable place, and usually the front-end users are not getting the freshest data. So now let's talk about the problems. The first problem is, as I mentioned, we are having a cron jobs running 1 hour to sync the data between the Amazon RDS and MongoDB. That means that the end users are not having a fresh data. And one of the biggest problems is that we are having a Mongo instance per database. That means that if we scale to every country of the world, that means that we'll have a lot of databases, and that means we'll have a lot of Mongos that we'll need to maintain. Also, why I'm mentioning Mongo as a problem, sorry, is that Mongo, until I think it was last November or something like that, was not a managed service. And that meant that our DevOps or SysOps were supposed to manage all of the MongoDB instances. And that can be a painful process. And one of the biggest pitfalls of this architecture is that actually if Mongo goes down, the application doesn't have anything to serve. And because it was maintained by our DevOps, they were supposed to maintain a lot of Mongos. And the last thing is not having API in front of the application. Basically, I can give a reasonable explanation why is that. If you want to have an API in front of the application, that means that we will probably need to have multiple queries to the application. And let's say that each query is taking up to 100 to 200 milliseconds. And on top of that, if you add the delay between our server and the actual end user, the speed of the application is not very fast. Now, the next reasonable question was why it was implemented like that. I cannot give you the proper answer to that, but I know that back in the days, that is 2014, 2015, all the major goal of the company was time to market, and the biggest challenge was to go as soon as possible out to market so we can get more share of the cake. And it was not we didn't pay a lot of attention to these kind of things. So I have presented the problem. we wanted to create a now new solution where we will have a more where we will have a much better where we will have much better and more scalable solution. So on the left side you can see that this was the actual situation. We have Spain, we have Sing application, we have MongoDB. If you can see that we cannot hear all of the countries, and this is how actually it looks. It looked like back in the days. What we wanted to achieve is that in the first iteration was we wanted to have a one sync application, and that sync application, instead of getting all of the data each 1 hour, just to get only the freshest data. How we are getting the freshest data, I'm gonna go in the slides after that. And the next thing, instead of using MongoDB, we wanted to use a managed service. And because we are at the moment, we are vendor locked, and I doubt that we will ever be non-vendor locked. On AWS, we are using the service Elasticsearch. And the reason why we choose Elasticsearch is that actually it gives a flexible query system where you can based on your indexes, you can create all of the page models that you want to present on the front end, and you have out of the box search engine, and you can make a lot of modification. On top of that, it's the searching it's really fast. And the last reason is that actually Amazon, as they're describing in their portfolio, they're saying that it will be that Elasticsearch will be available 99.999 something %. And when we were calculating that, that means that in a year, maximum 3 to 4 hours, the Elasticsearch will be down by unknown reason. Compared to Mongo, that because it was maintained by our sysops and DevOps, and it was not managed service, it was not automatically swapping the data and stuff like that. We were having a lot of issues like our websites were down, and we were losing basically money. So these were the ground rules. We want to have a fully independent system resilience. That means that if data layer is down, Elasticsearch will be down, and the user will always have the fresh data. Also, the scalability. It's easy to scale with Elasticsearch in this case, because even if I kill this service here, the data layer, that means that we will just restart the application, and application will continue to work. And also, we wanted to reduce the cost and complexity of the current system. Even though this system on the right is not the perfect one, I'm going to share you later with the reasons why it's not so cheap. So this is the initial architecture. We didn't want to go with the pull mechanism. We want to go more with the push. We want to be event driven. But as you all know, with SQL, you're not able to be event driven. So basically, you need to have some kind of puller who will actually pull the data and then push it inside your architecture. So this was the initial idea. We had Amazon RDS, and we know that MySQL database is usually write to binlog. Then our initial idea was to have a microservice, tiny microservice, which will get the changes from the binlog, process them, and then send them into SQSQ. Then we will have a scalable microservice system which we call MS aggregator, which will aggregate the data and store it in an appropriate place in Elasticsearch. Also, how the system will be scalable and how the system will continue to work without any problem. We will include Redis. That means that at the start, when we launch a new website, we will read all of the data, and we're going to store it into Elasticsearch. Problem solved. The next iteration, when some editor inserts some kind of voucher in the database, instead of on 1 hour refreshing all of the data, we will just get the delta of the last updated time before we have inserted into Elasticsearch. That means that if we set the timer each 1 minute, that means that the end user will get the data up to 1 minute late. So that means that he will get almost always fresh data. Also, this extra failover on the top right, is actually a paranoia mode, which we got suggestion from our DevOps sysops guys, which they told us that there is a situation where there has happened in the past where both Redis and the EC2 instance can be down. And for that purposes, we are also storing the information on S3. So even though if Redis is down and if this microservice is down, when we bootstrap both of the services, the application will know how to continue. But now what is the problem with this solution? The first problem is binlog. Because in binlog, you get every kind of message. And because you get every kind of message, you need to process that data. And in order to process that data, if it's not frequently used, it can be done really fast. But if you're working with a lot of with a lot of things, that means that this application will be slow, and initially it won't be tiny microservice. For example, if we have here one job which is updating all of the vouchers by some ranking, let's say, that means that they will update around 100K vouchers per country. If they update 100K vouchers per country, here all of those things will be inserted here, and then we will need to process the bin log data from the SQL database and then to send it to SQL. So basically, that was the initial problem with this architecture we wanted to change. The second thing what we wanted to change is that actually, if we build here, should we use a Docker instance or should we use a classic EC2 instance? For this logic here on the left, it's logical to use Docker, and that was the initial idea. But here there was no logic to use Docker because we wanted to have the application easy restartable, and also to scale it up and scale it down easy. So the initial idea was here to go with EC2 and here to go with Docker. So now this is the second phase of the architecture, because we didn't agree that we will go with this approach. Instead of having a bin log, we realized that actually we can use an Amazon RDS replica. That means that we will have an actual replica of the data of the production database, where we will have only read access. That means we will not be able to make any problem to the data. Instead of having one microservice, we decided to go with one EC2, which will actually do all of the things, and at the end it will process them into Elasticsearch. And this was actually the first step that we made correctly, and we're storing data into Elasticsearch. So with this architecture, we went live last year in May with one of our clients. Now the thing is, so far you are not seeing anywhere DynamoDB, but we will come to that. We will come to that part. So we're coming actually to that part, and this image here is basically adding more complexity to the current system. To give you more context about it, as you can see on the bottom side is the architecture which I was explaining initially. In parallel, because the business is at GAG, they wanted to expand the business, and they started to implement what we call it new architecture, where we wanted to have a full microservice architecture without using only AWS resources. That means that we had DynamoDB database as a storage. There we have some kind of microservice. We had an API gateway. We have a front-end Dockerized application, load balancer, a CloudFront. So now where is the complexity? The thing is that when I mentioned that they wanted to expand the business, is that, for example, instead of only vouchers, we wanted to try it out travel domains. That means that instead of only this showing vouchers, we wanted to have some kind of traveling websites, and we wanted to be served from the same domain. And the easiest approach to do that was to use a trick on CloudFront, where you will say, for example, if an URL contains some keyword, redirect to this load balancer. If application does not contain that keyword, or it's a default, then redirect to the whole database. And this was pretty good architecture. I mean, the top was pretty good architecture, but the main problem was that we were splitting the logic from two places. And because our application was evolving and we want to use the logic from the new architecture, and we want to use the page microservice instead of using the SQL, we were supposed to make some changes. Now to explain why we're mentioning so far the page microservice. In page microservice, we had all of the routes which we have in our application. That means every route which we are supposed to serve to the front-end user is stored there. And we have it on one place at the top and one place at the bottom. So for example, if I type like, let's go /travel/Goran, it will redirect to the top application. But if I go with /Goran, that means that it will redirect to the architecture at the bottom. So the keyword travel was redirecting to the top architecture, which was basically the hack. But the problem is, for example, what if if editor wants to create a new page, which will be named again /travel/Goran. That means that this application will never be available because the CloudFront will initially redirect the application to the new architecture and not to the old architecture. In order to solve so far I give you a little bit more context, so it will be easier for you to follow in the coming slides. So what we wanted to do, This is the second phase of the architecture. The top part is pretty much the same as I explained before. Here, and here we wanted to add integration with the new system. So instead of using the CloudFront as the hack-on CloudFront that will basically make route the applications through to one application or another application, we decided, okay, because this is a new architecture, we believe in this page microservice, we want to use it. In order to use it, we need to populate with all of the data which is here at the bottom in Amazon RDS. So the initial idea was that we want to have the big microservice, I will call it like that, which will go to the deals microservice, and it will store into Amazon DynamoDB. But the problem with this architecture is that if this microservice goes in wants to update the things, wants to update the page microservice, and the page microservice is for some reason slow or it's down or whatever reason, that means that we'll need to create some failover mechanism to the microservice. And with that, we will simply add more complexity here, and this will no longer be a microservice. It will become some kind of monolith. In order to bypass that, we decided to go with a little different approach. We'll use Amazon SQS, and that means that we're going to read all of the routes. We're going to throw them into SQS, and then with Lambda, we're going to save them into page microservice. That means that the Lambda will be responsible for storing the things into the page microservice. Why I'm mentioning here Lambda and why Lambda is connected to Redis, I'm going to give you an example. This is actually a fail on our side in the database, because we have data which is longer than 256 kilobytes. And the first limitation that we hit here is that some of the data we are not able to store the full event to the SQS queue. For that purposes, we are using Redis, which is in memory, and we are storing the old information into Redis. Then, in the SQS queue, we are sending only the ID. And then when that ID comes to the Lambda, because there is an option in Lambda where you can set that the producer of the events should automatically invoke a Lambda, we're getting the ID. And because we're having that ID in Redis, we will fetch that ID, and then we're going to store it into the page microservice. Now, to add even more complexity is that, but what if the data that we want to store into the DynamoDB is larger than 400 kilobytes? That is the second limit that we're having. We realize that in our database, we're having fields which are larger than 400 kilobytes. And in order to bypass that, we were having a check here on the data layer, which is actually checking if the problematic fields, because of course we know which fields can be problematic. Check those fields if they are larger than 400 kilobytes, store them into S3 and create a link. That link is inserted into Redis, and then Lambda is able to process all the information and store them into page microservice. Also, why we want to have here also one more thing, which is this is a bad solution, because this is an EC2 instance, and let's say that we want to insert 1,000 of routes. If you want to insert 1,000 of routes, that means that we will immediately bombard the page microservice. And if we don't have some kind of throttling, there is a really high chance that we will the page microservice will go down. And for that purposes, a new really nice feature from Lambda is that actually you can add throttling, where you can set how much in parallel invocations you can have on the Lambda microservice. And this was actually the second implementation, which went live last year. So now, again, to go with the problems, we answered why with 256 kilobytes. I said about throttling, and also in this case we are having a single truth for pages. Simple definitions how you can comprehend it is that all of the URLs are accessed from one place, even though that we are transferring from one database to another database. How everything looks from the code perspective. When we start the application, we get the last updated from Redis. Then we get the configuration, which queues that we are supposed to use, get the credentials from AWS Secret Manager, because we don't want to store any sensitive information like password to databases on GitHub. We know that Microsoft acquired it, and you probably know the reason. And here we have a bool. What is bool? Bool is a queue system based on Redis, which will solve you all of the baby problems. Initially, we thought that we are the smartest people in the world, and when we went with that approach, we realized that there is a lot of situation like, what if a job fails? If some job fails to read the data from MySQL and to insert it, what if there is some problem? For that, all of the baby illness are being solved by bool, and it has a really nice mechanism for scheduling jobs. And how we are scheduling jobs is that actually we are spawning a new node process where we execute the jobs that we want to store into MySQL. Why I'm mentioning jobs? Because in this case, on the previous example, we are talking about one database, but in reality, we have much more databases. I have taken the Pages microservice as an example because that will be the most easiest way to be understood. So the process goes to bool. Bool checks if there is an active job or if there is a not active job, and then stores it into, gets the data, spawns the job. Each job gets the things from MySQL, then store them into the Redis and send the SQS message, and then it's processed by the Lambda. Now to show you a little bit performance of the EC2 instance. Why we are using also an EC2 instance is basically you can see that the CPU utilization of our server is really low, which is actually good. This is on a regular basis. But the major problem comes when if you want to regenerate, you want to make a whole dump of the data. Usually we have that what we call regeneration process, and that regeneration process means that we want to get all the data from the whole MySQL database and store it into DynamoDB. That is a useful process because if we have some kind of remapping of the system, we will need a lot of muscle power, and for that purposes we are using T3 extra large EC2 instance for that microservice. Even though in reality it's using a lot less things, but from practice our conclusion was that let's spend $30 to $50 more per month, so we are on a safe side and we always have our application up and running. The second part is about the Lambda. So this is basically the diagram about the Lambda. Amazon EC2 sends to SQSQ. Here is the activity diagram and the logic that we have in the Lambda. And the interesting part here is that as soon as we insert the data, we remove it from Redis. And that means that our Redis doesn't need to be some crazy instance, but it can be, we consider it as a temporary storage, and actually that is the actual proper use of Redis. And the second part is that actually here we have also a fallback mechanism with a dead letter queue, that if something goes, if we are not able to insert everything into the page microservice, we throw it again at the end of the queue. When it needs to execute it again, we do it up until 5 times, and if everything is wrong, then we store it into the dead letter queue. And then tomorrow morning, when we get to work, we usually investigate what was wrong and what was bad. The libraries and frameworks that we used for the data layer was actually Express, TypeScript, Axios, Bool, TypeORM, and AWS SDK. We didn't use anything fancy because we believe that you don't need to use all the libraries in the world, because that is usually making your life more complex rather than simple. We're using only Express to wrap up the things. And the actual important thing is that we are using Bool, which is a really good queue system. And I highly recommend, if you have some kind of this kind of issues, or you will have this kind of issues, to consider it as for usage. Now I'm going to show you a little demo. Oops. I'm going to show you a little demo. So the first thing let me check if I'm on VPN. No, I'm not. 1 second. So for example, this is a dashboard. This is a dashboard of the data layer. I know that it's not the best design. For that, I can thank my colleague Vladimir. He's an expert in CSS. So first thing to start, we have here, as you can see, 1 job, 2 jobs, 3 jobs, 4, 5 jobs. And this is the Bool dashboard which Bool is giving you out of the box. As you can see here, it's showing you, is there any job active? Is it in a waiting queue? And this shows how many jobs have been completed. On the good side, for example, we can see that here for the home page, for the homepage, there has been some issue, and probably we have investigated an issue. What was the reason? Even though there is, okay, this is a good example. As you can see here, this there is the button activated, and that means that some job is at the moment executing. You can see that the vouchers, probably there haven't been any update, and the vouchers immediately went to completed. The same goes for widgets. In a couple of seconds, all of this will be inactive. Those are basically the jobs. What I was mentioning previously, even if something fails, that means that the next time, because the job was not successful, the last updated thing will not be, the last updated date in Redis is not going to be updated. That means with the next job, this will be fixed. For example, here is our data layer in Singapore, where we have three countries: Singapore, Indonesia, and Malaysia. And here also gives a good overview of what has been happening. This is a good example because none of the system is perfect. Of course, we will have some fail. That failure can be for multiple reasons. For example, if you have a deployment somewhere and it doesn't have a time to update everything, I mean, it's not able to reach microservice, it's gonna throw an error, and this will never pass. So this is the first thing. In order to show you a real example how this works, if I click on regenerate routes, there will be one job in a waiting queue, two in a queue. There is one which is active, and when the time comes, this job will be executed. That means that we have a settings in our data layers that we don't allow to have all of the jobs running at the same time with all of the heavy operation. Because if you go like that, we will simply block the system. As you can see, it went to the regenerate all, and now it's gonna regenerate. Usually the process usually takes around less than 20 seconds. But the thing is here, why it's taking 20 seconds to get this kind of information, is that we have a complex query. To show you another example is that this, one second, what was the name of the URL? That will be routes. One second. Oh, it is CG. Okay. This is an example of another version of data layer which we have for another client. And what I wanted to show you here is that if I click now on regenerate routes, you will see that almost instantly goes into completed. The reason for that is that here we are not having a complex SQL query, and because of that, it's usually taking around 500 to 600 milliseconds. The more complexity you add to the system, the more time the data layer needs to execute all of those things. Now to show you another example, I'm going to click again regenerate routes on France, and I'm going to open the SQS queue to see how the process goes. So if you want to make a full regeneration, that means that now the problem here is that Amazon changed their UI, and you're not able to have an easy way to show how many messages you have. Now we'll need to simply refresh. We will simply need to refresh and to see how much messages are at the moment active. And another thing is that we have the queue on the address in the DL microservice. That means that all of these things are happening at the moment. Okay, let me show. Okay, so for example, here we have 297 messages that need to be processed. And here we have a throttling on the page microservice, which they're being executed. Here it tells how many messages in flight are at the moment. And the last thing which I wanted to present is the Lambda. So for example, this is all of the things which I'm showing at the moment are on production system. So here we can see that we have some kind of hiccups previously. And you can see, for example, how many invocations we are having each moment. This Lambda is actually responsible for inserting to the page microservice, which at the end is storing into the DynamoDB. And usual average execution time is around, let's say, 285 to 400 milliseconds per hour. On the other side, here is the error success rate. So far, we had some issues. But at the end, they're going to the letter queue, and at the end, we are resolving them. As you can see here, for example, so far we have only one message. Probably for that purposes, we'll need to investigate it tomorrow. So now let's go back to the presentation. So let's go again with the second phase. here we're inserting into DynamoDB. The problem here, the next problem that we are having at the moment is Elasticsearch. So now let's go into the phase of scaling up. The problem is Elasticsearch. If you want to have a stable Elasticsearch system, you need to have at least 7 servers up and running. That means that you will have 3 control nodes, and you will have 4 data nodes. That means that in a single region. That means that if something goes down, you need to have at least 3 control nodes and 4 data nodes. So if something goes down, the application will be up and running. That is how AWS is telling you that they're giving you service which is up and running for 99.9999%. But the problem here is that actually you need to use 7 servers for the Elasticsearch. And in money, at the moment we are using T3 medium with SSD, something like that. For those 7 servers, we are paying around $600 per Elasticsearch. And we have so far Elasticsearch in multiple regions because if we have everything in Europe, if we have users from Japan, they won't get the data really fast. There will be latency in the network. The next thing that we wanted to do was that we wanted to remove Elasticsearch because we don't think that it's a future. There is another trending technology which is happening in the moment that's called AppSync in the AWS world, or in a world where you don't use AWS, it's called Graphql. The good thing about AppSync, AppSync is that actually you can have multiple sources and you can create the queries in a Graphql. That means that I can connect multiple DynamoDB tables and aggregate the data as I'm aggregating here for the Elasticsearch. This means that here I can add multiple things. It supports direct access to Dynamo. It supports HTTP requests. It supports multiple things. And on that purposes, we will aggregate all of the data and at the end serve it to the front end. Why we are doing this? Because if we have a multiple API calls, that means that the application will be slow. Of course, we have cache on CloudFront and that, but if for the first user before it's cache, it will give results in 3 to 4 seconds because it has some multiple things that needs to happen. And if we go with approach to have 1 or maximum 2 queries on the front end, that means that even for full site rendering, our application so far giving performance around 1 second to 1.2 seconds. And so far, and because we are fast, Google is ranking us much better than in the SERP. And now you can see here we have page, we have retailer, we have voucher, we have widgets. Basically, those are our entities, our models that how we want to proceed. Here they are aggregated and we are serving them to front end. That means that the sad story of this presentation is actually that as soon as we create all the DynamoDBs and we migrate everything to DynamoDB, that means that this whole presentation will fail. Why it will fail? Because we won't need all of these things which I described previously. Why we won't need those things? And the reason is that actually we will have already all of the data migrate from Amazon RDS to DynamoDB. And that is the sad story of this project. And this will be for 1 more year. Of course, I hope that I won't go out of job because I can migrate all the data. But the thing is that with this approach, with having some kind of lambdas and you having SQS and you have a service which reads the data from SQL, that is a good and stable approach to migrate the data from Amazon RDS to Dynamo. Also this gives a flexibility at least to the Angular team in our company, which will actually work on with an API, which of course we will have an API here for each of these tables, each of these entities. And when they say that they have migrated everything to use MySQL, to use DynamoDB table, that version of the API, we will simply drop this infrastructure, and we're gonna simply save a lot of money and change the data source from our applications to use DynamoDB instead of using Amazon RDS. Also, we will drop Elasticsearch. Why is that? Is that actually AppSync? The good thing for AppSync is that it actually charges you per number of requests. And if you have a lot of requests and you don't have a lot of data, you can simply add cache, and the pricing for it is much lower compared to Elasticsearch. because in Elasticsearch at the moment we are spending 500 euros. If you want to scale with the bigger SSDs and faster servers, that means that that can go a lot. And instead of 500 euros, our predictions that it will come to 2 to 3K euros per month. And with AppSync, our estimations was that it's going to be much lower. Okay, the complete picture. I haven't added here the diagram, but I will show you how everything looks like. So far, I have shown you a little glimpse, but in reality, this is how the system should look like. At the moment, I was presenting only for page microservices, but the same thing goes for another configuration, registry, keyboards, vouchers, retailer, all of the data models that we are having. And this is the whole architecture. And the things which I was presenting was that how we want to remove the old approach with MongoDB to manage service as Elasticsearch, and at the end, how do we want to move to DynamoDB tables. One more thing before I conclude my presentation. I want some acknowledgements to my colleague Vladimir Totochevsky for active development and triple questioning every decision that we were making. My colleague Marian Prishtel from DevOps for pushing me to lower the cost on AWS, because from time to time I was going wild with spending few K of euros. And at the end, to my engineering manager, Thomas Vaisuilesh, I know the proper pronunciation, I never learned it, for the support and believing in this project. I hope I was understandable. I hope that I was understandable and I was not that fast. Now it's time for question. Does anyone from attendees of the presentation has any questions regarding the presentation I just made?
Okay, let's see. Maybe wait for 1 minute or so that people can relax and start asking questions.
Is there anyone, or this was really boring and only interesting?
Hopefully not.
Okay, QA. Okay. Okay, the first question. What is different in cost of comparison to Elasticsearch and AppSync? Well, I can make an example now. AppSync cost. If I show here, for example, pricing example 1, if we have 5 million requests with $4 per million operation, that means that in total we need to pay $20 for 5 million requests. Data transfer charges, let's say that the data that we want to transfer is 3 kilobytes. That means multiple 5 million, that's around 5 million kilobytes. And this is a short example. That means that for 5 million requests with 3 kilobytes of data, we're going to spend $21. On top of that, we can add cache on top of AppSync, where we will simply, if we say that we want to use cache for extra large, which has 100 gigabytes of memory, it will give actually, I'm not sharing my screen. Oh my God.
Nope, you're not.
No. I was looking at the cost of on my screen, and okay. So as I mentioned before, this is a simple example from AWS, which is telling you if you have 5 million requests and 3 kilobytes per page per data transfer, that means that you will need to pay $21. On top of that, if you add cache mechanism, that means that you will pay, let's go, that we want to have a 25 gigabytes of storage, which is more than enough. If you go with simple calculation, 0.595 multiple 24 hours, multiple 30 days, we're gonna spend $500. That is if you use 25 gigabytes. In reality, we don't need that much of gigabytes to serve the users. 25 gigabytes will be more than enough for all of the users around the world. On other case, if you go with Elasticsearch pricing, AWS, if you go here, basically the price of the instance is pretty much similar, but instead of using EBS, which is basically regular hard drives, you want to use SSD. Let me find SSD, and SSD is expensive. And if you go with some instances, of course you will need to have 7 instances per region, multiplied by 5 regions where we have applications. At the moment, we are spending for 4 countries, we are spending around $500, $600. If you multiply that, that means that we're going to spend a lot more money compared to if you go with AppSync. And also the good thing with AppSync is actually that it has less aggregation compared to AWS. Any other question?
Anyone?
Okay. AppSync, why we didn't go with from the beginning? The reason for that is that back in the days, that was 3 to 4 years ago, we were not that experienced with AppSync. It was not released by Amazon, and Graphql was pretty much really new, a hot topic. And we went with something which is something which was we had a little bit more experience with. Okay, this is an interesting question. So basically, if we have a database of a large scale, will it be in out of favor to include Dynamo? Depends from your needs. I cannot give a concrete answer here. That depends what you want to serve at the end. At the end, why we choose DynamoDB? The only reason is because it's basically you can consider DynamoDB not as a regular database, but more like a hash map. That's how I consider it. You have a key and you have value, and in that value you can put whatever you want. And because it's serving it's a hash map, the access time will be really fast. And as Amazon is telling us that it's gonna be less than 10 milliseconds, and our main purpose of our application was that we want to serve speed. That was the reason why we went with DynamoDB and not with something else. If you ask me about that, that's actually perfect for our use case. Also, it's a managed service by AWS. It can offer you a lot of scaling, throttling, and all of that fancy things that we want to have in our system. But on the other side, that means that if you have some kind of system and you want to migrate to Dynamo, you don't need to migrate everything. You can migrate only the things which are crucial for your business and where you need speed. Our major reason was that we want to go with we want to get the data as fast as possible to the front-end user. Does this answer to your question, or? I hope that I gave a proper answer. If not, you can always drop me an email. Tanya probably at the end of it, we're gonna share my email. So everyone who has any questions and doubts about the things that we have been building or needs more information, I will be more than happy to give you all of the answers. Any other questions? Or only 3 people were listening to me what I'm talking about?
Okay, I mean, if we don't have any other questions, I guess we can sum up and finish the first Tech Tuesdays event powered by Intertec. I would like to say thank you to Kopa for his presentation and taking the time to participate in the event. Thank you to everybody who joined today in this hot summer day and who are supporting our initiative. More fun and new things and events are coming up from Intertec, so stay tuned. Follow us on Facebook or LinkedIn or Instagram, whatever is your weapon of choice. Anyhow, not to drag this any longer, once again, thank you and hope to see you. Okay, we just have a comment that the presentation was very, very cool and very good. So anyhow, thank you once again, everybody, for joining us today, and see you next time. Bye.
Thank you. Bye-bye.